edge to avoid trying to guess what's going to happen in the next 1,000 years. Okay, so I'm going to begin with the following wanted poster. Wanted, a theory of the mind, an attempt to understand the mind. How would you go about understanding the mind? Well, there are lots of ways of going about understanding the mind. I'm going to describe one way. It's essentially the way of Western civilization, and I'm going to be concentrating largely on Western civilization. So it's a Western civilization way of understanding the mind. Not surprising, with that lead up, I'm going to tell you that the first people that did it, that made the first attempts, were the ancient Greeks, 300, 400 BC. That shouldn't come as a surprise, because most of Western civilization can be traced back to the ancient Greeks. What usually comes as a surprise to people is when I then say that the way the Greeks tried to answer the question is through mathematics. The moment I say that, the response is usually, why? Why on earth would anyone think of using mathematics to understand the human mind? Well, the reason people find the statement that we're looking for a mathematical answer surprising is because most people don't really know what the answer to this question is. What is mathematics? To most people, it's something to do with numbers. It's sort of balancing checkbooks and sort of that kind of thing, okay? Well, that's only a very, very small part of mathematics. The only definition I know of mathematics that captures what people like me do for a living is we study the world through patterns. Mathematics is the science of patterns. Okay. What kind of patterns then can a mathematician study? There's all kinds of patterns available for mathematical study. Before about 500 BC, 600 BC, the popular conception of mathematics being something to do with numbers was actually accurate. Insofar as there was any mathematics then, it really was the study of numbers. People were looking at number patterns, counting things, okay? It changed when the Greeks expanded the horizons of mathematics to include geometry, because geometry has very little to do with numbers. It's about shapes. It's the study of shapes, visual patterns. Okay. Mathematics evolved over hundreds of years. Developments were made, but it didn't really enlarge its scope in any noticeable way until the middle of the 17th century, when along came Sir Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany, and they figured out how to expand the horizons of mathematics to study motion and change. Whenever you've got motion and change, you can use mathematical tools to study those patterns of motion and change. The method they invented, is what we now call calculus. By today, by the end of the 20th century, the patterns studied by the mathematician include patterns of symmetry, patterns of position and plasticity that we call topology, patterns of dynamical systems, chaos, probability, statistics, and the list goes on. One thing I haven't included, but let me include it now, is that there's no reason why we shouldn't look at the patterns of reasoning, of thinking, of language, and communications. Indeed, if we do that, we might be tempted to think that we can build machines with which we can converse, like the one that was up on the screen as you were coming in, the HAL 9000 in the movie 2001, which incidentally, when the movie was made in 1968, they went to great pains to try and project forward to 2001 and get the technology right. As I'll try to convince you of towards the end of today's session, there are good reasons to believe that a lot of the things that were thought possible back in '68 are practically impossible, certainly impossible given present technology, by which I mean even making the machines faster and bigger probably won't do those kind of things. Okay, but that's projecting ahead to the end of today's session. So if you're a mathematician and you want to study the mind, what you're going to be doing is try to find the patterns of thought. lots of ways of looking at the world, right? Physicists look at the world and see physical patterns. Chemists see chemical patterns. Biologists see biological patterns. Painters see certain kinds of aesthetic patterns, patterns of texture and hue and color. Dramatists, playwrights and so forth, novelists, they see various patterns of human interrelations. You can look at the world through lots of different kinds of spectacles, and each one gives you a different way of looking at it. What's unique for the mathematician is we mathematicians have the ultimate throwaway society. We look at the world and we throw everything that's real out of the window, leaving what Bishop Berkeley said of Newton's calculus, leaving the ghosts of the recently departed quantities. We throw everything away. It's a nice phrase, isn't it? The ghosts of the recently departed quantities. We throw the reality away. We're left with this shadowy framework, these abstract patterns. If you think of mathematics in that way, first of all, it seems a lot less scary than it does when you think of solving equations. And secondly, it gives you an indication why you might use mathematics to go into this thing between our ears to try and understand the patterns of thought. Because we can't see them. We can measure some of the sort of brain waves, but we can't really get inside our minds. We can introspect and we can listen to other people. We have to find very abstract ways of describing and analyzing those abstract patterns of mind. Okay, going back to the Greeks, there were actually two different schools of Greek logic. One was Aristotle, who said, if you have a piece of reasoning, a logical argument, then you can reduce it to a series of basic steps which he called syllogisms. I'll give an example in a moment. Okay, so it was a divide and conquer approach. Incidentally, the Greek logic, the mathematics produced by the Greek logicians was actually used by the Greeks to some extent and then by the Romans as a means of training public orators, politicians and so forth. It was an exercise of the mind that was supposed to develop the ability to reason. Okay, so you look at arguments and you say, to be logically sound, you have to have one assertion, then another one, then another one, then another one, and they have to follow in a logical sequence. They have to be logically coherent. Okay, and the question is, what has to go on at each step to give you logical coherence? Aristotle gave one answer. The other Greek school was what we call, there was a Stoic school, and they did what I would call a building block approach. They said, when you're building an argument, when you're making an argument to someone, when you're reasoning, what you're doing is you're taking basic assumptions, basic propositions, and you're combining them in interesting ways to produce richer information, to produce more information. Okay, so here was the Stoic approach. Take basic assertions, what we would now call propositions, combine them in various ways, like an erector set, to construct an argument. So we've got two ways of going about it. Let me just, in very brief detail, show you a little bit, first of all, of Aristotle's syllogism. From time to time, I'm going to put up a slide where the print is a little bit smaller and it's a little bit fainter. This is the fine print, okay? When you go to rent an automobile, you fill in the front, and if you turn it over on the back, there's the fine print. It's in a small print, and it's grey. Now, that's meant to tell you, take a glance at this, but you won't need it unless we get into litigation. Just sign on the bottom line, okay? It's the same here. Take a look at it, get a sense of it, but the rest is not going to depend on it unless, at the end of the talk, someone comes up to a microphone and we end up in litigation. Okay, so here's the first fine print. One of the most commonly cited example of Aristotle's syllogism, and this is the little rule of reasoning that's supposed to make you go from one bit of the argument to the next. He said, well, it's a bit like arithmetic, where you write two numbers, one under the other, you draw a line, and then you add them up or you multiply them and get an answer. He says, you write one assumption, and then you write a second assumption, then you draw a line, and then you write the conclusion. And he says, all logical reasoning should be split up, possible to split it up into a sequence of these things. Well, that example is so obvious and so simple that if I only presented that one, you would think, why are we making a big deal of what Aristotle did? Well, let me give you another one. Okay. There's the question. What's the answer? Supposing we have two assumptions. The first, no counsellors are bankers. The second, all bankers are athletes. Aha. I've got to be honest with you, I've gone from the easiest known example known to mankind to the hardest known example known to mankind. This will stump practically anyone, so I'm not going to leave it up there without the answer much longer. There's the answer. Are you any wiser? Well, there it is. Okay. These are just examples. What Aristotle was really interested in was the abstract pattern. What are the general patterns of reasoning? And the point about the syllogism is we've identified a linguistic pattern, a certain pattern of language which, if we use it, will give us a logical argument. All, some, or no, some things are something else, etc., etc., etc. If you look at all the possible combinations of all, sums, nots, and so forth, there are actually 256 possibilities, most of which, you'll be pleased to know, do not give you a logically sound reason. Only a small number are actually logically valid, and Aristotle identified the correct ones. He actually made a little slip, and he said some were correct, which we now know are not correct. But by and large, he got it right. I mean, it was really remarkable. Over 2,000 years ago, someone used mathematics to go inside the human mind and say something about human reasoning. The Stoics, in some senses, the Stoics invented computer science in 2000, in 500 BC or something, 2,000 or more years ago. Because what the Stoics developed, their kind of logic, what we do now is implement their logic in silicon and we sell it for about $1,000. Okay, or more. Okay. It's a forerunner of what we now call propositional logic. Incidentally, there are two reasons why Stoics didn't have computers. One was they didn't have the technology. Well, I guess there's three reasons. One is they didn't have Bill Gates. The second one is that they didn't have the technology. And the third one is that they didn't have algebraic notation. And I'll come back to that later. Okay, what they said was, well, theirs was an atomic approach. Just like in sort of when we're doing physics or whatever, you can sort of look at atoms and say they're sort of basic things that you put together to form molecules. They said arguments are made up of propositions and they're basic things you can put together. A proposition is any old statement that's true or false, take them as atoms, and then look at the ways of combining them. And they were very clever. Mathematicians, by the way, can produce very impressive stuff. That's because we have this secret. The secret is, if we don't know how to do it, we don't mention it. So why did they only use and, or, not, and entails? Because they were the ones they could handle. They didn't mention the others because they couldn't do it. Okay. And then today we would use notation, and here's another bit of fine print. We would use notation to just abbreviate those things. We use P, Q, and R to talk about propositions and so forth. Okay. Incidentally, there's not a lot of algebra coming, and it's all in the fine print for those of you who feel nervous at the sight of these things. And then they looked for consequences. And I've put two rather simple consequences, one of which tells you that it doesn't matter which order you say things if they're both supposed to be true, and the second one tells you how you can deduce something from two others. Okay. That gives you the general flavour of the thing. So it remained for about 2,000 years, until in the middle of the 19th century, this rather stern-looking gentleman came along. This is George Boole, an Englishman, who in 1847 succeeded to do what the Stoics couldn't do, and what nobody in the interim could do, although several people tried. What he was able to do is apply algebra to the human mind. He had the idea and published it in 1847, then he republished it in 1854 in a book with a very long title that we usually abbreviate to the laws of thought. So he was using algebra, not just sort of mathematical methods of looking for patterns. And remember, the Greeks were essentially looking for the patterns. It wasn't really algebraic. Middle of the 19th century, Boole was able to take algebra out of the sort of classroom, if you like, and into the human mind. He applied algebra to thought. How did he do it? He took basic atomic propositions, just the way the Stoics did it. He denoted them by letters, So this is just like regular algebra. X, Y, and Z denote numbers. P, Q, and R denote thoughts, human ideas, propositions. And he developed the algebra. And then he showed how to solve equations. If you have an ordinary equation with numbers and you solve to find out what X is, you're getting a number. X is a number. When he has an equation with P's and Q's and R's and things and solves to find P, he gets a logical conclusion on the basis of some premises. So in Boole's system, solving the equation is finding the logical conclusion. Is my client guilty or innocent? Well, let's just solve the equation and decide it. We don't need a jury, we'll just use the algebra. Also, for reasons we'll probably get to later, today's courts tend not to use algebra. Though maybe they should. We'd at least have other things on the news. Okay. I wonder what he's referring to. Are you ready for some more fine print? Just a little bit more fine print. Okay, here it is. Here's some of what Boole found out. Wow. Okay, there's the fine print for you. I've probably split the audience into two completely different groups. There are those people who say, now he's getting down to business, right? I mean, these are the guys that work at Intel. Right, okay, the real thing, yes, glad we came. There's another group, probably in the majority, who say to themselves, oh my God, oh dear, we're only 5-10 minutes into it, and we got a page full of math. How much longer do we have to go? I mean, well, why do we do this? Why do mathematicians do this to ourselves and to everybody else? Okay. Well, remember what we're trying to do. We're trying to get at ghosts of recently departed quantities, very abstract patterns. We're trying to get, at the moment, into the mind. If you're dealing at that degree of abstraction, you need an abstract notation. We're not the only people who have that problem. There's another well-known group of people excuse me, another well-known group of people who also have to deal with abstract patterns, and they need an abstract notation. And that's those guys. Aha! I don't know why that looks less intimidating. To most people it doesn't. To me this scares the life out of me. When I was at school I learnt about musical notation. I know the rules, but I never was able to figure out how to read music. To me, I look at this and it's just gobbledygook. I don't even know who wrote it. Well, actually I do because I made the copy, but just by looking at it I don't know who wrote it. I'm sure there are lots of people in the audience who first of all know exactly who it was that wrote this, and secondly, who they look at this and they don't see the notes. They go right through and in their mind a piano is playing and they can hear the music. Because anyone who can sight read music doesn't see the notes, right? You go straight through the notes into that musical pattern that's created in the mind. And then you can take that pattern and put it into a keyboard and we can all hear it. And at that point, I can enjoy it too. Okay. It's the same with mathematics. When a mathematician looks at something like this, we go straight through the symbols. Mathematicians are not people who enjoy dealing with symbols. We're people for whom the symbols don't exist. We go straight through the symbols and into that mathematical pattern that's created in the mind. I can use the phrase music of the mind, and that's a very metaphorical way of putting it because it's not sounds, but a mental pattern is created corresponding to it. The payoff, well, there are several payoffs. One payoff is that when you get the abstract description, you can often see patterns that you wouldn't have imagined were there. Let me, alongside these equations, and this is still fine print, so you just have to look at them, you don't have to understand them, it's like the music, but let me put up alongside it the rules of arithmetic. And wow! There's an awful lot of similarity. You don't need to understand what it says to just realize that familiar properties of numbers on the right-hand side, you get the same pattern. The P's and Q's and R's on the right are numbers, the ones on the left are propositions, human thoughts. At this degree of abstraction, patterns begin to appear that you might never expect were there. So this is one of the powers of this kind of notation. You can simply see the pattern coming right out of the page, and you might not have suspected it was there. Boole did suspect it was there. Boole got it on the page, And so Boole was able to show how you could use algebra to make logical deductions. And if we don't ascribe the Stoics the honor of inventing computer science, then we better ascribe it to Boole, because from then on, it was simply a matter of the technology. Okay, so we're now up to the middle of the 19th century. We're getting close to the present stage, right? Late 19th century, we have what we'd call modern mathematical logic developing. The people that developed it were, there's a whole bunch of people, Giuseppe Peano, Gottlob Frege, Charles Sanders Peirce, Bertrand Russell, all people whom we would now regard as part mathematicians, part logicians, part philosophers, whatever. Okay, a whole gang of people beginning to get interested in this issue of patterns of the mind. Then coming into the present century, the period from 1900 to say 1980 is what I would call the golden age of mathematical logic. I mean, it just blew out. It was just tremendous. There was an enormous amount of activity. Lots of people became logicians. They would call themselves logicians. Departments of mathematics and philosophy began to have groups working in logic. Huge amounts of work. We had mathematical grammars of formal languages. And I'm just going to throw some buzzwords out at the moment to give some indication of the way this thing blossomed out. We have Alfred Tarski developing a theory of meaning, what it means when you talk about meaning in mathematics, what we would now call semantics. I'll probably start using from now on the two words syntax and semantics. Syntax is grammar, how you put words together to form sentences, for example. Semantics is what the meanings are that you get when you do that. Okay. Kurt Gödel, whom many people have heard of, is almost an icon of the age, almost as famous as Einstein, and indeed in later life a colleague of Einstein, since immortalized in a very dreadful movie whose title I've forgotten, in which we have Einstein, Gödel and somebody else. Okay, did anyone see that movie? Okay. Gödel coming along showing that the syntax and semantics were equivalent in mathematics. The very famous Gödel incompleteness theorem, which shows that there are limits to what you can do with logic, even within mathematics. Alan Turing, during the time of the Second World War, or before the Second World War, developing the theory of computation, making the possibility arise of creating machines that can reason and think, first electrical machines and more recently electronic machines. And we also have significant applications of these logical techniques within mathematics itself. So a period of 50, 60, 70, 80 years with enormous activity. Definitely the golden age, a remarkable success story, but it came at a price. It came at a price. The price we paid for the golden age was that our logic only worked within mathematics. Remember, we began 2,000 years ago trying to understand the patterns of our mind. What do we end up doing with this work that I've just described? We end up describing the patterns of the mathematician's mind when the mathematician is doing mathematics. Now, okay, well, that's fine for those of us who are mathematicians, right? But what about the rest of society? Yeah. Well, around 1950s, some people began to ask that question and said, look, we've got off track here. It's been great fun, we've had a ball, it's been a gas, but let's go back and let's look at the rest of mankind. Let's look at the rest of people who think. Okay, because there are other people out there besides mathematicians. So there were attempts from the 50s onwards to apply logic, or at least the ideas of logic, to real thought, and then to go from there to construct machines that can think. Okay. Indeed, it was out of this thrust that the idea of HAL 9000 came up, the possibility of machines that could do control, that could speak, that could understand us, and so forth. Simultaneously, and I mean simultaneously, both of these had huge impeti from MIT. We have AI coming out of MIT very largely. We have studies of language using mathematical coming out of MIT with Noam Chomsky. Okay, so we've got two threads coming out here. It's worth pausing and noting that. Historically, we have people looking at language and reasoning as all one part of the same thing. It's all in one bag. Within the last 100 years or so, language and logic began to come apart, so that by the 50s, you have logic looking at reasoning, and you have language dealing with language, and they're becoming separate. You have departments of linguistics and departments of AI and logic. I would say that was one of the big mistakes historically, and I'm glad to say that those two groups are coming back in many instances, because I think that hampered a lot of progress. Because I think language and reasoning are two sides of the same coin. Okay. Picking the first of those themes first, in AI, in artificial intelligence, we have John McCarthy, who gave the field its name. We have Marvin Minsky, who was actually the main consultant on 2001. At the time, he was the head of the AI lab at MIT. We have Newell and Simon, and the kind of things they did was develop problem solvers, chess-playing programs, control systems that exhibit intelligent behavior, expert systems that could diagnose illness and so forth. A lot of technology came out of that. A lot of very useful technology came out of that push. The idea, incidentally, behind developing AI and expert systems, when we reduce it to its simplest description, is you do three things. You feed the algebraic rules of logic into the computer. Once you've got things written algebraically, it's easy to get them in the computer. So you feed the rules into the computer, you code the relevant information into algebraic language, and you feed that into the computer, and then you hit the go button, and you let the computer use the rules of logic to make deductions on the basis of those facts. And the rest, again, is implementation. That's the idea behind building machines that can think and deduce. Put it through logic, get it in the machine, let the machine do it. Remember, when you get it into algebra, doing deductions is just like doing arithmetic. Well, we all know that computers can do arithmetic. We can buy a $10 calculator at the drugstore, it'll do arithmetic. Do it Boole's way. Do it the Boole way, and you get logical deductions. Okay. That's AI reasoning systems. What Chomsky was doing, and I'm going to go into the fine print mode here because I'm going to give you a little bit more detail about what Chomsky did. Chomsky asked himself the following question. He said, he first of all said the following. He said, language is a very complicated thing. If I'm going to study it scientifically, I'm going to have to break it down and again do what the mathematicians do, find the bits that mathematics will apply to. And he made a very shrewd decision. He said, the part of language that the mathematics is most likely to apply to is answering the question, what sequences of words do we recognize as grammatical sentences? And what sequences of words do we recognize as non-grammatical sentences? So he posed a very specific question. The reason for posing the question, well, there were two reasons. One is that he figured out that mathematics would work, and the other one, he said, it's rather remarkable that by the time we're 3 years old, we all acquire the ability to recognize a grammatical sentence and to produce a grammatical sentence. We don't have to be really taught it. We sort of listen in as small children, and we quickly get the message. Something is going on in the brain. We have some propensity to be able to tell grammaticality from non-grammaticality. We might not have much of a vocabulary. We might not have very much interesting to say, but we get grammatical sentences very, very quickly. So what's going on? What patterns are we recognizing subconsciously when we recognize a sequence of words as a grammatical sentence? So he tried to describe those patterns. Well, wait a minute, you say. You can have sentences as long as you like. You can have ifs and thens and ands, although, whether, notwithstandings. You can have a legal contract where no one can understand the sentence, even though we recognize it as grammatical. Surely there are infinitely many patterns. And indeed they are. You could make the sentences longer and longer, more and more complicated. There's no end to the complexity of the patterns. So that's a little bit of a problem. What do? Well, if you're a mathematician, you sort of look elsewhere for the pattern. You say, okay, the actual patterns of the sentence, there's lots of them. What about the mechanism the brain uses to figure out whether it's a sentence? What about the rules that will generate the pattern? He wrote down algebraic rules that describe the patterns whereby we put words together to form sentences. So here again, we've got the use of algebra to describe something going on in the mind. And here is, in one fell swoop on the fine print, a little bit of one of the grammars that Chomsky wrote down. He called these sets of rules grammars. Why not? That's the word we usually use when we're talking about grammatical sentences. He said things like, let's look at the first one. If you take a definite noun, notice that there are no equal signs. These are not equations. These are rules for producing phrases and sentences. So the arrow tells you you're producing something. If you take a definite noun phrase like the man, and you follow it by a verb phrase like entered the room, you get a sentence. DNP is the symbol he used to denote a definite noun phrase. Anyone. These are algebraic symbols. They're like X's and Y's and Z's. But he used different letters because he wanted to say we have things called noun phrases, we have verb phrases, we have verbs. So we'll have letters to denote those. And you get a sentence. I'll just read one more aloud and leave you to look at the rest. The second one says if you take a verb like entered and you follow it by a definite noun phrase like the room, then you get the verb phrase entered the room. And he started writing these algebraic rules down and said you can put any verb in where there's a V, you can put any noun in where there's an N, and if you do that, you'll get something that the human mind will recognize as grammatical. He knew, incidentally, and I'm not sure that everyone does know, so let me tell you, he knew that sentences were not the same as sequences of words that make sense. When I was at school, I was told that a sentence is something that makes sense. Well, that's not what a sentence is at all. A sentence is something that we recognize as a sentence, and Chomsky has a very famous example to show that we, human beings, recognize as sentences things that make absolutely no sense at all. Here's his example, okay? Colorless, green, ideas, sleep, furiously. Colorless, green ideas sleep furiously. However you cut it up, it can't possibly make any sense. It's oxymoronic everywhere. Colorless green makes no sense. Green ideas, no sense. Ideas sleeping, no sense. Sleeping furiously, no sense. You can put words together in such a way that they don't make sense anywhere you look, but it still sounds like a sentence. Our mind recognizes the pattern. Colorless green ideas sleep furiously. Yeah, that's a sentence. We're recognizing the very abstract pattern, and it takes something like Chomsky's grammar to describe that pattern, because it's got nothing to do with whether it makes any sense to us. Okay, now we're almost up to date, and I'm going to try and take us to the point of projecting into the future. I've been giving you the success story. AI had a lot of successes. Chomsky had a lot of successes. This was great stuff. This was mathematics and science doing its thing as it's been doing for 2,500 years. Let's look at the assumptions that we made, either explicitly or implicitly, and certainly in Chomsky's case, these were very explicit. We're focusing on what I've called syntax. We're focusing on the symbols. We're ignoring what these things mean. We're ignoring the context. And we're assuming that expertise in reasoning, and we're assuming that the use of language can in fact be captured by rules, because that's what the mathematics was doing. In AI, you get the rules and you put them in the computer. In Chomsky's case, you write the rules down and use them to investigate grammaticality. So those were the assumptions that are being made to buy us this advance. Around the 70s and 80s, things began to look problematical. The typical story in both AI and linguistics was you start out trying to build some system, either a reasoning system or a system that can understand language. You feed in a little example and it works. And then you start feeding in more complicated data and it suddenly doesn't work. What happened in the 1970s and 80s is what in my book, Goodbye Descartes, I called the logic wall and the language wall. We came up against these walls that we didn't see, and we came up against them very fast. Things were going fine, and then you suddenly hit this wall and didn't seem able to make any progress. Okay, occasionally you could glimpse over the wall and might be able to put a little hole through it, but by and large the hole seemed to prevent any advance. Let me give you some indication of why I think we hit those walls. One of the problems is ignoring meaning and context. Why is it a reasonable approach to do what people did and ignore meaning and context? Because scientists have been doing that kind of thing since time began, or at least since science began. Okay. What do we do in physics when we're trying to study motion? We say, okay, motion can be complicated. Let's ignore friction. Let's assume that these objects are perfect spheres or perfect blocks. Let's ignore the complicated shapes, and let's do some mathematics. So we ignore friction, we ignore the shape, we have point masses, perfect spheres, and so forth. We go out, we write down our equations, we solve them, and we get conclusions. Okay, very, very successful. Then, when we've done that, we come back and we say, well, we'd better make a slight adjustment to the answer to allow for friction. And we'll make a slight adjustment to allow for the shape. And it works. Mostly it works. What more could you expect? What more could you ask for? Whether you can expect it's another issue, but we ask for it, and in physics we get it. In most of the natural sciences, this approach works. We can ignore the complicating factors, do the mathematics, put the complications back as extra terms to account for the discrepancy at the end, and we get the answers we want. Okay. So it works in the physical universe because we can approximate it with these idealizations. Now the question is, can we do the same thing? Can we pull the same trick when we're dealing with language and reasoning? Can we include complicating things like meaning and context? If you can, and if you can add them in at the end, then the approach will work. I think there's a lot of evidence to indicate that we can't do that. I think there's plenty of evidence to show us that meaning and context are not add-ons, they're built in right at the ground level in language and reasoning. If we throw away meaning and context, we're throwing away the baby with the bathwater. Let me give you I'll give you a couple of examples. Supposing you were walking along and there was a building site, and there's a sign on the building site that says, hard hats must be worn on the site. You know what to do. You know that you're not allowed on that site until you've found a hard hat and put it on. Right? We all can read this, we all understand it. So you're at the building site, better find a hard hat, put it on. Okay, now you go to the shopping mall, and there's a sign that says, dogs must be carried on the escalator. Do you look around for a dog, pick it up, and get on the escalator? Well, you may do. I mean, I don't know. I mean, I haven't been in Oregon before. I don't know what people in Oregon do. But I'll tell you, down in California, for all that we're regarded as figures of fun, we don't look for dogs before we get on the escalator. What's going on? The sentences are the same structure. The syntax is the same, right? It's the same thing going on. We know, because of the meaning and the context, that these things are saying very, very different things. Okay. Meaning and context are very fundamental in even understanding what's going on. Okay. Let me give you some more examples. And these are a rich source of entertainment, because this is the Jay Leno section when I'm going to give you one or two ambiguous headlines. Okay. Here we go. Police begin campaign to run down jaywalkers. Yes. Oh, I wish they would, yes. Okay, here's one for all those parents and high school teachers and elementary school teachers in the audience. Safety experts say school bus passengers should be belted. Yes, preferably every day, I guess. Yes. Okay. That's my favorite. That was from the time of the Falklands War. Yeah. These are all real examples. They were all in the newspapers. Yeah. Well, okay, so that's one for the Brits, okay? That's my favorite. Okay. How about one for the Americans? How about this famous one? Reagan wins on budgets, yes, but more lies ahead. Yes. Yes. Who said meaning and context don't matter? By golly, yes. Two sisters reunited after 18 years at checkout counter. Okay. Yes. Though I have to say, we have a local Safeway where this is almost true every time I go in it. Okay. Panda mating fails, veterinarian takes over. Well, okay. The moral, of course, is context matters. You can't ignore context. If you ignore context, wow. I mean, if you looked at these and think about these, it's not just that the meaning changes. In some of them, the context determines which words are the verbs and so forth. British left waffles on Falklands. Where's the verb? It depends on the context and the meaning. So the context and meaning can affect the very syntax that Chomsky's grammars studied mathematically. So it's not that you can go in with the mathematics and deal with it at syntax and then add the semantics. The syntax and the semantics affect the very things, the context and the semantics, affect the very things that you try to study when you do syntactic theory. Okay. Incidentally, the ambiguous headlines, I mean, take those out of context and they're amusing. They're not unusual. I mean, ones that are so funny are somewhat unusual. But you just pick up a newspaper at random and look through the headlines. I'd be very surprised if somewhere in the newspaper you can't find at least one ambiguity. This is not an unusual phenomenon. If you start looking for it, you'll find it everywhere. Okay, so meaning and context, they're in there from the ground level up. Recognizing that fact, in the 1980s, there were attempts still being made, to rebuild logic with context built in from the ground level up. There were several attempts. One attempt was actually made, and is still being made, by John McCarthy, one of the people who invented artificial intelligence. He has a theory of contexts. Another one I'll mention is the one that I got involved with. Came out of Stanford in the late 1970s, 1980s. It was a theory called situation theory. Again, it was an attempt to redevelop logic, but including context. One of the books that was mentioned in the introduction, 1991 book, Logic and Information, was a description I made at that time of where situation theory was, how far you could get when you try to include logic, when you try to include contexts in logic. So there were attempts in the 80s to incorporate context. Something else happened in the 80s. There was a shift in emphasis. Okay, we're still trying to understand the mind, we're still trying to understand language, but there was a shift in emphasis from logical reasoning as this step-by-step process to a much more holistic thing, to try and get at what we think is going on when we introspect on our reasoning. And there was another shift from language as a vehicle to the whole issue of communication. Language being part of communication, but communication being much more than that. Okay, so various shifts in emphasis were taking place in the 1980s as we began to try once again to get inside our minds using tools of mathematics and whatever else we can lay our hands on. These days, when people start to do this process of getting into the mind, we take account of a whole bunch of important factors, or we should take account of these factors. I've mentioned context or contexts because there's usually lots of contexts. We should certainly take account of that if we want to understand the mind and language. We should take account of psychological features. We need to take account of cultural features. And again, the reason being that these are not just add-on parameters. These are not friction. These are built in at the beginning. We can't keep using divide and conquer science if we want to get inside our minds. We need to start looking at the structure of conversations. Okay. What's going on when two people converse? It's not just words going backwards and forwards. We need to look at the role of emotions. Some very interesting recent work. There's been a whole rash of books recently with the word emotion in the title. Actually, the publishers love this because every now and then a word pops up that helps them to sell books. A few years ago, it was discovered that if you're writing a book on physics and cosmology, you better put God in the title because that sells books. Think about it. There's a whole range of them out there. There are two buzzwords now for selling books on the mind. One is consciousness and the other one is emotions. Lots of books coming out with one or both words. Actually, I'm not sure if there's one with both words in, but there's been lots of books with two words, with one or the other word in. Okay, so we need to start taking account of these things. I'm actually not going to get into the emotion aspect during the presentation, although if people want to ask about it later, I'm game for a discussion on that stuff. So long as we don't get too emotional, of course. Okay. There are psychological features then. Let me look at the second one. We've dealt with context. What about psychological features? Well, it's not that we've discovered something that no one's thought about, right? People have looked at these things. Psychologists have been looking at these features for years. There's a whole bunch of work by Tversky, Kahneman, and the list would go on and on and on. Lots of people who've looked at the influence of psychological features on human reasoning. Okay, it's time for a little bit more fine print. Some years ago, a group of physicians was presented with the following question. They were told the following. Imagine that you were, well, they were physicians, so they didn't have to imagine it. So you are a physician faced with a rare disease. The disease is expected to kill 600 people. There are 2 treatments available. Treatment A will save 200 people. The rest are going to die. Treatment B, the alternative, gives you a 1/3 chance of saving everybody and a 2/3 chance of not saving them. And the question is, which of the 2 treatments do you choose? And the physicians overwhelmingly chose A. Given the option, they thought, I don't want to run the risk of killing everybody. This gives me the chance of saving 200 people. I'm going to go for it. Fine, except another group of physicians was posed the following remarkably similar looking question. You are a physician faced with a rare disease expected to kill 600 people. Treatment A will kill 400 people. 600 minus 400 is 200. Let's remember that, okay? The rest will survive. Treatment B offers a 1/3 probability that everyone will be saved, and the rest is the same. All we've done is we've switched the emphasis from the 200 dying, or is it being saved? I forget now. The saving 200 and the killing 400. With that little switch, most of the physicians in the second group chose B. There's another twist to this one, because 1/3 of 600 is 200 and 2/3 is 400. So the mathematical answer is, makes no difference whether you choose A or B in either case. So if you're a mathematician, you know, you just toss a coin and choose one of these things. But most people with serious illnesses do not come to mathematicians for treatment. Though when I compare my salary to those guys, that, you know, what was it that Tom Lever said? I'm a physician who specializes in diseases of the rich. Right. Okay. Okay, just one more example. This is a one that's very familiar to everyone. You don't need to be a physician to realize this. Most people, when they get on an airplane and they put the safety belt on, I don't know if it's most, but a lot of people feel a sort of twinge of nervousness. You know, they grasp the armrest and so forth. They get in the car and they fasten the seat belts and they give it not a second thought, but we all know the statistics. The statistics tell us we're overwhelmingly more likely to die in the car or to get injured in the car than we are in the airplane. So human reasoning processes, human rationality is not independent in any way of context, meaning, and psychology. The psychological aspects of the way we behave are really quite significant. The moral, second moral, first moral was context and meaning matters. Second moral, psychology matters. It isn't just friction that you add in at the end. The third one of the issues was cultural features. Well, the psychologists have been looking at the psychological features for years. All we need to do is look at their evidence and then try to incorporate it into our mathematics and our science. The sociologists for many years have been looking at the culturalists. I mean, that's what they do in sociology. I wish they'd told me years ago, because for many years I had no idea what they did in sociology, but now I know. About 30, 40 years ago, a group of sociologists broke away and gave themselves an incredibly complicated name called ethnomethodology, which is an interesting subject. Very difficult to read, very impenetrable stuff, I find, but there's some interesting stuff in there. What they did is they said, look, some of the most interesting things about people are the things they do without any thought at all. The way they use words, the words they choose, the actions they perform, the things we do quite unreflectingly. One of the leading people in ethnomethodology is a man who tragically died very young, Harvey Sachs, at UC Irvine. In 1972, he wrote a paper, a sort of seminal paper in the subject, in which he talked about, in his words, the fine power of a culture. And he observed that the way we interpret language, the actions we perform, are remarkably similar from person to person to person. It's not, as he said, that these things are sort of, there are similarities here and there. He said, by golly, it's almost the same from person to person. He found the level where the patterns were so regular that to someone like me, he was doing mathematics. That's an interesting thing to say, because ethnomethodologists, to a person, insist that their work is miles away from mathematics. I always look at what they're doing and saying, you folks are doing mathematics, you're just not using X's and Y's and Z's. Okay. For example, no one has any difficulty understanding this, and I'll bet everybody has a mental picture that's almost identical of someone fainting, some people going by and rushing to help. I could have written another pair of sentences with the same structure where you wouldn't give it the same coherence. For example, why are you assuming that they're the people passing the person by? You're assuming that they're passing him by. They could be passing the stadium a mile away. They could be rushing to help somebody else. In this example, every one of us assumes it's all coherent, it's describing the same scene. Similar examples go different ways. It's not that the words are guiding us, it's that we have an enormous cultural background that these words trigger. We know what it's about. If I say, do you have the time? Do you say yes or no? Well, you might. But you're breaking the laws of cultural civilized society and behavior if you do. This is the way we frequently ask someone to tell us the time. What we're really saying is, tell me the time. Why is it that we ask it this way? Well, it's certainly not logic, because the logical answer is either yes or no. Cultural answer is that you tell someone the time. Likewise at the table, can you pass the salt, please? Okay. Well, if you don't believe me, go home, and the next time someone says, can you pass the salt, say yes or no and see what happens. Children, don't try this at home. Right? Or, for example, supposing a little dog came bouncing across the stage. I'd be inclined to say, hey, look at that puppy. I could have said, look at that canine, or I could have said, look at that animal, but you'd think I was a bit odd. If the thing was a puppy, why not call it a puppy? The question is, why is it a puppy? Why isn't it a canine? Why isn't it a dog? Why isn't it something else? Why do we use that word? On the other hand, if I was at home and the puppy was the dog that we'd just bought and the dog was called Rover, it would be very odd if I said, look at that puppy. I'd say, look at Rover. And if I didn't, you'd say, what puppy? All I can see is Rover. From a logical point of view, it doesn't matter whether you call it that dog, that canine, that puppy, Rover. They're all talking about that dog. As far as culture-free logic is concerned, it's all the same. But in people terms, the difference is phenomenal. You will understand them very differently depending on the words you choose. And again, in Sachs' terminology, the fine power of a culture, this is so built into us that we don't even reflect on it. We instinctively know there's a right description at the right time. Okay, so there's the third moral. Culture matters. There's one more to go, since I'm ignoring emotions in the presentation, and that's the structure of conversations. And there's a whole branch, actually both psychologists and sociologists have developed areas of study called conversation analysis, where they look at the patterns in conversation. Okay, so the goal of conversation analysis is to identify the patterns. Now, we may think that when we're conversing, you know, all bets are off, we can talk about whatever we like, we can talk about things in whatever way we can. The answer is yes or no. We have a lot of freedom, but conversation is very brittle. If you go beyond the bounds of what's permitted by the abstract rules that are sort of built into us, or that we evolve, or we learn, or we're acculturated to, if you go outside of those, things break down very rapidly. An obvious example was when transatlantic phone calls began, when none of us were really familiar with them, and there was this little second and a half or whatever it was delay. It wasn't that that made conversation difficult. The darn conversation just kept breaking down. We found we were speaking at the same time, there were long pauses. We're getting better at it, we're getting used to it. But those little fractions of a second or second or two delays, until we became acculturated and accustomed to them, they broke conversations down. There wasn't that much freedom in the structure of the conversation, certainly from the point of the timing of the responses. Among the early people in ethnomethodology, in fact, who looked at the structures of conversations, there was UCLA's Harold Garfinkel, and I'm going to mention two examples that he gave a class back in the 60s. One time he said to his class of students, he gave them what I call the fill in the details exercise. He says, the next time you go home and you have a conversation with your spouse or partner or whatever, write down what you both say. Transcribe it. Then go away, put what you've transcribed on one side, and on the other side of the page, fill in all the details that I, as your instructor, would need in order to understand what's really going on. Well, okay, so the students went away, and they wrote down these little passages, 3 or 4 sentences each, short passage, and then they filled a page or so, filling out the details. And then they gave them in to Garfunkel and said, here we are. And he said, well, wait a minute, I'm going to go through your explanation. You haven't really told me what's going on here. I don't really know what's going on here. I don't know what... And he went through and said, you need to fill in more details. Go away and fill in the details, because I don't have the background that you have to understand this. So away they go, and the 5 sentences become a page, become several pages, and they come back and he says, well, I don't really know all of the background to this, and I don't know the background to that. Because at that point, the students say, hey, give me a break, I'm not going to do this. This is far too difficult. It is not going to end. And if you try it, and if you don't believe me, go and try it. You start doing that, you're in an endless process. If you and I play that game, and I'm Harold Garfinkel, and you're doing it, I'm going to win. Because you're never going to give me all the details. I'm always going to be able to say, you may know that because of your experience and your cultural background, but I don't know that. Give me the details. The other exercise he gave them, and incidentally, I've got some fine print data with me if afterwards anyone wants to see some of this, and some of it's hilarious, was the follow-on. He said, go back, when you meet your spouse or partner this evening, whatever they say to you, respond literally. Oh, don't try this one, whatever you do. As I said, I've got the fine print with me. We can look at some of it later. It's a gas to read about it. You don't want to be in the scenes that developed. Sometimes at the very first response, it was brutal. I'm not sure if we'd allow exercises like this nowadays. It breaks down quickly. People know about what's allowed and what's not allowed in a conversation. We don't know it explicitly, but by golly, the fine power of a culture builds it into us in a big way. Okay, so culture matters. We can't get away from it. Okay, so here we are, we're faced with trying to do the same thing again, to look for those abstract patterns, to throw away reality and see what the patterns are. But this time we're trying to do it by incorporating all of these things, these various features that we can't ignore if we want to make progress. Okay. Where are we going to get? What's the chances of making any success, making any headway if we do this? Because it seems a very challenging prospect. Well, I want to say, at the moment, the historical developments, the things up to the present day, have essentially depended on what I'm calling the modern Cartesian assumption that in some senses the mind is a computer. Okay, that's sort of embedded in our culture now. It's embedded in our linguistic metaphors that we use every day. We talk about processing information, interfacing with each other and all that kind of jargon stuff. Okay, isn't that great, interfacing with each other? Oh, God. Horrible, horrible, horrible. Okay. I should say a little bit more about this because, sure, the mind is a computer. Lots of things are computers. We can compute with an abacus. We compute with a slide rule. To say that the mind is a computer is an observation. I'm not denying that. Lots of things can be computers. They don't have to be made out of silicon and put in a box with grey on it and a screen and so forth. It depends on what you use it for. You can take a Macintosh and you can use it as a doorstop if you want to. It makes a very good doorstop. And I guess if Apple's stock keeps falling, that might be what we all end up doing with our Macintoshes. But you can use it for that thing, and if you use it for that thing, it's a doorstop. It's very good to be used as a computer because engineers have designed it to be useful as a computer. So there's an issue of what things are designed for, what they can be used for. Sure, the mind is a computer. The question really is that all the mind is? Does that really capture the mind? Or we could even be a little more kind to scientists like myself and say, well, is it enough to base your science on the assumption that the mind is a computer. Hitherto, we have done either explicitly or implicitly, and if we do, then what we do in our science, the goal of our science, is to determine the programs or the rules of that science. Okay, so there's where we are. That's history so far that I've sketched out in the previous 45 minutes or so. What would the alternative be? Well, here's a suggestion. The alternative is to think of the mind not in terms of a computer, but that it's an evolved, complex, adaptive system that can recognize patterns, and recognize patterns is what I'm going to concentrate on. I'm going to get away from computing and say that what human minds do is they recognize patterns. They can categorize things in the environment. They can recognize categories across the environment. They can see the patterns, and they can react to those categories in a given context. Okay, so let's try and think of the mind in this way. And if we do that, question, what's the corresponding scientific goal? What are the specific goals? And how do we go about trying to achieve those goals? Well, it seems to me there are two possible goals. There's a long-term goal, which would be the original goal. Let's see if we can do it again. Let's try and develop another science of the mind. Let's not be naive about science. Science is not about finding the right answer. There's never been the right answer, and I don't see any reason to assume they're going to be. Science is about finding a better answer. What do you mean by better? Well, more useful. We feel better about things. We feel we understand things better. We can build things better. We can design things better. You decide what you mean by better. Science is about finding the better thing. Okay. Supposing we do that, what might we expect it to look like? What would we expect in the long term? Well, looking into the future is a dangerous thing, but the millennium is almost out. Everyone's doing it, so let's do it. Natural science, we know that to become a scientist, what do you have to do? You have to, first of all, you take a lot of math classes, right? You have to go through mathematics to get into science, because that's the glue that holds it together. That's the skeleton that our sciences hinge upon. What would a science of the mind look like that's capturing cultural features, context, all that stuff, where we're assuming that the mind is a complex adaptive system, etc., etc.? Well, let me make a suggestion. Mathematics, I think, is still going to have a role to play, although it's going to be a different role. Okay. And people like myself are going to have to get used to the fact it's a different role. Mathematicians have used to being king of the hill, right? Science had to obey the rules of mathematics. They had to come and we had to solve the problems, or they solved them for themselves using mathematics. It had to obey the rules of mathematics. We made predictions about outcomes and futures and so forth. I'm not standing here and saying that we can do the same thing for people. We can do it for groups of peoples. We can make predictions about societies, how they'll vote, what kind of things they buy. When we look at whole societies, patterns emerge, patterns of behavior which are quite reliable. One of the most interesting sciences now, and it really is, I think, a science, is the advertising business. By golly, do those guys study how we respond en masse, or on the average, or in 60% percentiles or whatever. Do they study in great detail how we respond? Now, the amount of scientific investigation that goes behind an advertisement for a breakfast cereal is really quite phenomenal. Okay, they're timed down to the fraction of a second, how long you're going to see the spoon of Wheaties and things. It's interesting stuff. But at the level of individual people or small groups of people, there's no hope, surely. At least I don't think there's any hope. I don't see how mathematics can work in that way. So let's give a name to the mathematical role that we might see being played in these sciences of mind, or this science of mind. Let's call it soft mathematics. Soft as in software, etc. Soft from the Burroughs novel, Soft Machine, the human being. So this would be the mathematics of the person, or the mathematics of people. Then we would be studying the patterns of individual human behavior. I'm actually not inventing anything here. I'm not claiming to have invented soft mathematics. I'm not saying that anyone has sat down and thought of soft mathematics. I'm saying people have been doing it for the last 50 or 60 years. We've called some of them psychologists, we've called some of them sociologists, ethnomethodologists. What have they been doing? They've been looking at the patterns, the abstract patterns of people's behavior. They've been doing the experiments, they've been looking at the data. They haven't been calling it mathematics at all, but to me as a mathematician, that's one way of looking at what they've been doing. They've been looking for those patterns. So let's just give it a name. We'll make sure we don't call it mathematics, because I think the role is clearly very different. It's not about precision prediction in the way we are in the natural sciences. But I think there's a huge role to be played by this kind of analysis, by bringing together. And let me just say something about bringing together. I think what's holding us up at the moment is the fact that something that's been very successful hitherto, we've made progress as a society by bifurcation, by divide and conquer. We've specialized. As the years have gone by, we've got more and more specialized. We've become specialists in this, specialists in that, subspecialist, subspecialist. That's been very successful. It would have been even more successful if all those specialists had somehow been able to maintain the ability to communicate. But it ain't happened. Not only do the sociologists and the mathematicians almost never communicate, they can't stand the sight of each other. I mean, go to your nearest university, go into the math department and say, how many of the sociology faculty do you know? How many did you have coffee with this morning? When did you last meet them at the photocopy machine, etc.? It doesn't happen, almost never happens. Progress has been bought, as always, at a price, and I think now we'll be paying the price until we either can communicate across these disciplines, or much more likely, recut the disciplines in different ways, carve them up in very different ways. Interestingly enough, where I see the most advances being made in these interdisciplinary areas are not in our universities, they're in the computer industry, in the design industries. You go to Xerox PARC, you go to Apple, you go to Microsoft, you'll see people thinking and moving across disciplines all the time. Why? Because they're not trying to advance science. They're not trying to advance physics or sociology or anything. They're trying to build better artifacts for people to use. And if they need to blend some sociology with some psychology, then they'll go away and try to do it. So I think we're being led, as so often in history, by technology. It's a technology-driven push towards a possible new science. Okay, so that would be the long-term goal, the original goal of a science of the mind. That last remark about the computer industries and technology industries, that was bringing me on to what I think is a short-term goal that we've already seen progress towards, measurable progress towards. What I'm going to call mind cultivation. Okay, using soft mathematics, or what I'm calling soft mathematics, and that's just a name I'm giving to a certain view of things that are going on in lots of different disciplines. By calling it a name, I'm trying to bring out the fact that sociologists are doing it one way, psychologists are doing it another way, computer scientists are doing it another way. They're all doing something, and there's a commonality across them. And so I'm giving it a name so at least we can talk about it. Using soft mathematics to develop ways to prepare the minds of experts, and I'm going to acknowledge that we have usually very little idea where our own expertise comes from. Experts can make decisions and do things that they find very difficult to articulate. One of the difficulties in building expert systems, the most difficult part, was trying to get the experts to explain how they did things. Develop ways to solve problems and make decisions, even though they may not be able to articulate the way they arrived at the answer. Acknowledge that evolution has developed our minds to a stage where we can develop enormous expertise by practice, by feedback, by a whole variety of mechanisms. Part of those mechanisms being learning certain rules, but usually when you're an expert, you forget the rules and you behave in a different way. So our mind as an adaptive system can develop expertise that we cannot capture by rules. Let's see if we can find ways to prepare the mind so that expertise has the best chance of success. Let's try to prepare the mind so that we can manipulate context and take advantage of experience. Okay. What do I mean by that, just as a closing remark? Look around us and ask ourselves which people have the most skill and ability to be able to take human experience, human knowledge, human culture, manipulate it to their ends. Well, dramatists can do that, playwrights, novelists can do that, movie makers can do that, skillful rhetoricians and politicians can do that. We can develop skills to take people's experience, to take their cultural backgrounds and manipulate them and convince them of things and to give them insights, tapping into this rich experience. Those people can do that. They can do it because they can tap in to experience and context. They've developed the skill to do it. Scientists and mathematicians can tap into other things. We can tap into the ability of the mind to manipulate symbols, to manipulate abstract patterns, and we can do things with that. So we've got these two strands, two kinds of manipulation. Manipulating the human experiential aspect and manipulating the human logical aspect. Why keep them apart? Maybe we can't blend them, but maybe we can. It seems to me that the time has come to give that a shot and to try and develop, call it soft mathematics if you like, call it something else if you'd rather. If you don't like the word, call it something else. But that, it seems to me, is where we are now. That's, I think, where we're going to be going in the future. It's not a blind prediction, because I look around and I see what's going on in the various computer labs and going on in some of the university departments, and I see this happening. Is it going to succeed? Who knows? But that's surely why science is so exciting. That's why most of us go into these things, because it's the unknown, and by trying to get into the unknown, we may not achieve the goals we think we're going to achieve, but we always get useful side effects in the process. So at that point I'm going to stop, and I'm being prepared to answer any questions, or try to answer any questions that anyone would like to ask. Thank you for your time.
I'm going to go to the mic, or I will ask a question. Somebody upstairs there? Go ahead.
Terry?
Yeah, go ahead.
I'm interested in ways in which you can use the soft mathematics to help experts solve problems better and make better decisions. One thing that occurs to me, and I imagine you talked to Roger Shepard at Stanford, because he did all that work in multidimensional scaling, but multidimensional scaling seems to me a way that you could use a soft mathematics to help people become aware of aspects of their thought process that they didn't know otherwise. Is that the kind of thing you mean, and what would be other examples?
Okay, other examples. Here's one that during the past week, as we've been driving up and down Oregon, Terry and I have been bouncing between ourselves. If you're a scientist and you want to get funding for a research project, what do? You write a research proposal. If it's a big funded project, you're probably going to be called in front of a board to defend the research proposal. So you're at a table with your research proposal and the board examining you. You know, and they know, that the moment you're funded and you start the work, problems are going to arise, you're going to change direction, you're going to end up doing something maybe having nothing to do or very little to do with your research proposal. Similar example, suppose you want to start a business. You go to a venture capitalist or a bank and you want to start a business. What are you going to be asked for? A business plan. You're going to work on a business plan. You're going to go before a board and they're going to ask you how the business plan is going to be put into operation, what you're going to do if this happens, what you're going to do if that happens. You know and they know that the moment you get the money and start to set up the business, problems will arise, situations will change. You'll end up doing something probably very different from the original business plan. You'll probably find out you weren't building X, you were building Y, your market wasn't A, your market's going to be B. Everything's changed. Why then do they ask you to do the business plan? Because writing the research proposal, writing the business plan, that's the first step in the process. It's showing what? That you've thought about starting the business or the research proposal, you've thought about the problems that might arise, you've gone through the exercise of writing the proposal or the business plan. You've demonstrated that you have the ability to start the process. In the interview stage, you'll probably go through enough question and answering to demonstrate that you can indeed respond to the kind of changes that might arise once you're out there developing your product or doing your research. In other words, it's not the business plan that matters. It's not the research proposal that matters. It's the mind cultivation that's involved in going through the process of preparing those things. What does the manager, the bank manager, or the venture capitalist, or the research funder want to know? They want to know, is your complex adaptive system primed to deal with the kind of problems that's going to arise? Do you have the ability to adapt and change and push your expertise in the directions? So writing those things is mind cultivation. It's preparing the way. The process is what counts, the action of going through it, not the actual product of it. Incidentally, that makes what I'm talking about, that second short-term goal, is not really a science goal. It's an engineering goal. Because engineering is not about sort of finding the answer. Engineering is about building something or getting something to work. The long-term goal is the science. The short-term goal is essentially an engineering one. There are other examples, but there's just one instance of... Actually, I'll put up some fine print, because I've said several times that there's been attempts in the past to develop soft mathematics. There was one back in the late 1960s in the field of conversation. Someone, in fact Paul Grice, a very famous philosopher, wrote down, or what Grice did was try to do for conversations what Euclid did for geometry. Euclid in his Elements wrote down the axioms for geometry. Grice started to write down the axioms for a conversation. This is soft mathematics. He didn't call it that, that name wasn't there. Why? Euclid's Elements, the idea is that on the basis of the axioms, you can prove absolutely, rigorously for all times that Pythagoras' theorem is true, etc., etc., etc. So the idea in mathematics is you can prove things as it is in science. Here, these are not called axioms, they're called maxims. Grice isn't saying you follow these rules all the time. Grice isn't saying that you have to follow these rules. Grice was saying, give or take the odd bit of free play, this is what governs conversation. If your conversation is within line of the maxims, it'll be a successful conversation. If you break them, one of two things will happen, and this is where it got interesting. If you break them, the conversation might break down. Or if you break them, you might be able to say one thing and mean another thing. Grice actually did what I will call proving soft theorems. He proved soft theorems. He proved theorems like, if you say this, you mean that. If you say pass the salt, please, if you say can you pass the salt, you'll mean pass the salt. He looked at what he called conversational implicature, saying A and meaning B, which as we all know is not an infrequent phenomenon. Okay, so here would be another example that would fall under the rubric of what I'm calling soft mathematics.
Okay, let's go. There's somebody over here.
Can you reflect for a minute on the role of emotions and the importance of emotions in the development of artificial intelligence? And perhaps if you have the minute, reflect a bit on the book by Antonio Damasio, who was a speaker here last year, talking about the role of, it was in the title of his book, Emotions, he had it in the title. So that general, how important is emotions, and will it be a limit as we attempt to develop true artificial intelligence?
Right. In fact, the thing that his book and mine share in title, we both have Descartes in the title. His was Descartes' error, mine was Goodbye Descartes. I guess Descartes is the third key word to sell a book, right? You have emotions. Well, okay. You know, I'm a cultural creature. I mean, I'll bow with the cultural pressures. Okay. First of all, I think the best answer is to say, for heaven's sake, read Damasio's book. There's another book called The Emotional Brain, I think it is, by Joseph Ledoux, that's just come out. There's a book by Daniel Goranson called Emotional Intelligence, which is a sort of an easier read. Been a lot of interesting stuff recently about the role of emotions. Let me just mention one thing, and this actually, if you were here last year with Damasio, he probably mentioned this, because some of the interesting stuff in his book and in some of these other books and articles is the following, that we sort of have this belief, this Cartesian belief, I guess, that you've got emotions and you've got logical reasoning, and by golly, if you want to reason logically, you'd better keep the emotions out of the business. Keep those two things apart. In fact, we tell each other, I mean, you know, we're having an argument with our spouse, and the worst thing we can say is, don't get emotional. Let's reason out logically, okay? Which, of course, usually has the effect of making the other person even more emotional, right? I'm not going to tell you how I learned that lesson, but believe me, I did. Okay. What Damasio and other people have been finding is that they've looked at people with brain damage. Now, you can have there are certain unfortunate individuals whose brain can be damaged in such a way that what we might call the seat of the emotions, the amygdala or various other parts of the brain, that can be knocked out. And you can have individuals who give them a logical reasoning test or some mathematics or a logical puzzle, and they'll solve it. I mean, they have logical ability. No doubt about it. You can measure it and test it with logical puzzles. On the other hand, their logical module or whatever you want to call it has been knocked out, and you can observe that they really have no emotional responses. They don't have emotions. And then you step back out of the little puzzles and you try to see how they operate in the real world, and you never see more illogical behavior. These people do things that could kill them, that could damage themselves. Take away the emotions, you might leave the ability to deal with logic. You can do in certain cases, but the result is not a logical person. In the metaphorical sense, the result is a person for whom logic and reasoning seem to have been thrown out of the window. As you were coming in, they were showing part of 2001. I'm not sure which part they showed, but there's an interview with the BBC reporter early on in the movie, interviewing Hal and interviewing the crew. And at one point, the BBC reporter says, Hal, in some of his responses, seems to behave in an emotional way. Do you think that Hal has consciousness or emotion? And the crew member, the crew leader, Dave, says, well, Hal was programmed that way to make it easier to deal with for us people, but I'm not sure whether that means he really has emotion or not. That, incidentally, was a portrayal on the screen of a test known as the Turing test for intelligence and machine behavior. The idea being, if something looks like a duck and waddles like a duck and quacks like a duck, what the hell, call it a duck, okay? If you can get a system on a computer that looks intelligent, behaves intelligently, exhibits intelligence completely, why not call it intelligent? Now the question, of course, is can you do that without somehow getting genuine emotion in there? I guess the answer is nobody knows, but the evidence that Damasio and others put forward is that it looks, at least in the case of people, that emotion is really built in. And that was why it was one of those features that I listed in my list of having to have emotions. I think you're going to have it. The reason I didn't talk about it was I don't know any more about it than I've read in those books, and so my advice is to go and read those books.
Okay. Let me just, I was going to ask a couple little things just to try and pull a couple things together. I was thinking of the HAL thing. Now, obviously we have computers. I know one, there's in the baggage, where the baggage goes from the airplane to the proper place. And there's a thing where I've seen a deal where the guy can sit there and say, you know, left, right, you know, center, and the computer will send the bag to the left, right, or the center carousel, and you can do that. So this computer can understand the words. Obviously, the person has to talk within a very limited frame, and maybe it needs to be reoriented every once in a while. And there will be things like that going on. It seems to me that the trick comes when I ask the following question. So we can gear that up to various levels that we know that we can do limited things. I could be saying 1, 2, and 3, of course, or I could just be going beep, 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 or beep, 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 and I'd be doing the same thing. The issue that you're raising, I guess, is that the computer can respond in a kind of simple behavioral way, but is going to have problems understanding the meaning of what I'm saying. I'm thinking of how. I'm thinking now, would I go on a Jupiter trip with the computer, and to what extent would I do it, even if it has soft mathematics in it? Now, here would be my fear. I'm going along, and in most contexts that I'm in, the computer's going to do just fine, and we can program with some emotional type behavior, and it's going to go really fine. And then something else is going to happen that the engineers didn't anticipate. Some context, some situation is going to arise. And I'm going to say, computer, we need to do da-da-da-da, and he's going to misunderstand what I'm saying because he's really just a set of algorithms, and unless the engineers were able to anticipate unique situations and that he would understand the meaning of what I was saying at that time, that he's not going to be able to do that. So I don't want to put myself in a situation where any computer in any future is going to be expected to understand a unique, meaningful situation, which another human could, but the computer couldn't. Am I on the right track here? Mm-hmm. Is that kind of what you're saying?
You're on the right track. I'm not quite sure what the question is that I'm going to answer.
Well, I'm trying to make sure whether is that right? I mean, is that what you're saying?
Yeah. One difference between machines that we build and the people that we are is that to us, our survival matters in a very, very fundamental way. We have evolved as survival machines. I'll begin to sound like Richard Dawkins if I'm not careful. And I guess we both do have English accents, but let's not go too far down that path. Okay, we are survival machines. You can, of course, program a computer so that it sort of has a little subroutine that says, do everything to make me survive, or, but ultimately it doesn't matter to the computer. You know, you pull the plug and it stops, and it doesn't matter just to the computer, and nobody else cares either. But we are individual people who want to survive, and we're linked to each other. And now we are getting back into this grey area of how the emotions come in. What is it about us? Emotions have to do with being developed as survival machines, passing on the genes and so forth. So I think there's a great difference. I think we can, if we follow that path, we're pushing ourselves back into raising the question on the assumption that the human mind is a computer, even a sophisticated computer. And I think that's not really the question. I think that very framework to raise the question is very misleading. I think let's start thinking of things as survival machines, adaptive, complex systems. In other words, take an evolutionary account rather than the computer account. And I think if you go into that framework, I don't even think you sort of raise the issue. I think the issue just drops away as a non-issue. I may be wrong, but that's from my present stand in that framework.
So your challenge to the industry, what's been going on, and for Minsky and all these guys that thought we were going to get these things, you're saying now after 20, 30 years, looking at the evidence, that there's some qualitative chasm that we're not going to jump over there.
Yeah.
We can approach, we can mimic, but we're never going to get the independent thinking computer that can communicate in a reliable way in general.
Yeah, although let's be careful. What I'm not saying is that we'll never build machines that can do these things. I'm saying that we're not going to build things that we would call to computers. I'm saying it's not an issue of more RAM or faster speeds, faster processing. That's not the issue. When we start talking about getting there by increasing the power, which does occasionally work. It worked in playing chess. The trick to playing chess was to abandon AI and to let the computer play chess its way, which means I'm big and I'm fast and I'm efficient and I've got one hell of a memory. And once we realize that, we can get machines that can beat almost any of us at chess. Okay, so that's one way. But
there could be other ways.
but I don't know whether there are other ways. I mean, how can anyone know whether there's another way? But in the case of developing computer technology, I don't think there's enough in there. And I don't think you can fake emotions and survival mechanism in a sufficiently deep way. That doesn't preclude another technology. I think the myth is best captured in an example. I forget who first, I think it was Bar Hillel, who said, when you start thinking that the key is to just get bigger and faster machines, that's like fooling yourself into thinking that you can reach the moon by building taller and taller ladders. Yeah, you can see yourself getting closer to the moon, but it ain't going to get you there. Forget the ladder, go away and build a rocket. I don't see how anyone could stand on any stage and say, we can't go away and do another thing. For one thing, we know that there's a very simple and pleasurable way of producing thinking machines that want to survive.
Okay. Gotcha. Right over here. Babies.
I'm very interested in the problem of the 200 patients who live and the 400 who die. Would you mind putting that back up?
The 200 and 400, okay. It's here somewhere. Okay, at least it was here somewhere, and unless science has done something remarkable tonight, it should still be here. Okay, let's move this out of the way. 1, 2, 3, 4. Unfortunately, it's the fine print, and my eyesight is not what it used to be. There we go. So there's the fine print.
Okay. The top section. That works for you because you removed from this scenario the culture of being a physician. And also you made the assumption that the outcomes are actually the same, they're just in disguise. But speaking as a physician, I was very interested in this because I'd go for the way my colleagues did. I would do that every time. I would even be suspicious of a colleague who went for treatment B. I might think he was an imposter who was really a mathematician, because the first scenario is biologic. It's real life. There will be some survivors and some who are not. The second outcome is not biologic. Nothing that we do ever affects a series of patients the same way. We would never have 600 survivors or 0 survivors. We would be very suspicious of any series that was published which purported to have such a result. So the culture of being a physician would cause us to respond in that way every time. So it kind of makes the point, I guess, that you're trying to make, which is that without culture, then syntax and meaning suffer.
Right, yeah, and let me echo that. I think I would say that, you know, I may have a whole score of books and papers that say that I know about logic, but if it came to applying reasoning about helping humans to survive, then what I'm saying is that there's a culture of physicians out there. They have expertise. They might not have the same logical skills I have in logical reasoning out of context, because that's not what they do. But if I'm ill, I'm going to go to a physician who's got the cultural background and the expertise, and I don't care whether they can write it down in laws of logic, because I don't think my survival is going to depend on the laws of logic. It's going to depend on that instance on the expertise of that individual, whether that individual can articulate it or not. So yes, I'm agreeing with that. I'm going to echo that and saying that expertise is what it's all about, evolved expertise that we can't necessarily articulate, we can't capture. We can at best help develop by trying to manipulate context, by putting scenarios up that help people to learn. This isn't rule-based learning, it's not rule-based logic, it's what we might call case-based. It's putting people in familiar positions, familiar situations, so that this adaptive, complex adaptive network between our ears adapts in ways where the expertise is going to be more useful. And again, that's the engineering goal. Is it going to save me? Is it going to build a better gizmo? Is it going to improve the system? Down the line, we may get scientific understanding. But right now, the payoff for doing this kind of thing, the payoff in terms of social structure of trying to break down some of these disciplines that we have separating ourselves, I mean, it's no longer just C.P. Snow's two cultures. I mean, we've got dozens of cultures out there, and none of them are talking to each other. I mean, if there's a moral in any of this evidence that I've been presenting, it's that we are hindering progress enormously by having all of these different cultures. We need to put the whole lot back together again. That's got enormous implications for education and so forth. But that's a whole different discussion.
Can I tag one thing on that? What he just did, this was a fairly, if you like, context-independent example. Yep. He then went back and started doing something which is very close to what you're suggesting is the steps in the direction of soft mathematics, yeah?
Yeah.
He started pulling out context and some patterns that are there. Is that correct? Is that
oh, yeah.
kind of what he was doing there? Okay.
As I say, soft mathematics is not something I'm inventing. It's a name I'm putting to a behavior that, looking at the world in through mathematical eyes, and I don't have any other kind of eyes except a mathematician's eyes, looking at what's going on, I see certain similarities. And just so we can discuss them, let's call them soft mathematics.
Yeah.
Whether or not you can actually write down an algebra is another issue. Whether you can start calling things X. Well, sure, you can start calling things X, Y, and Z. X can be a culture, Y can be a context, and so forth. You can do that. You may be wasting your time, or maybe you'll be in the same position Boole was when he wrote down in algebra the rules of logical thought, and you put alongside them the rules of arithmetic, and you think, hey, there's an awful lot in common here. Maybe I can learn something by looking at arithmetic about logic and vice versa. So just because something seems that it's not amenable to an algebraic study doesn't mean to say you won't buy something by trying to capture those patterns with letters in an abstract way. You may not, but why make the decision before you try?
Right. Let's go, sir.
Yeah. Quite a line there.
Yeah.
If I can get this microphone. You talked a few minutes ago during your lecture about when you were talking about conversational analysis, and you teased us with an example that you didn't actually develop, and that was the assignment that had to do with the be literal exercise. And being a teacher in the area of communications, you left me with my mouth hanging open, waiting to hear those examples so I could see if I wanted to do this with my class or not. So, could you share that?
Surely. Okay. Here we go. Subject goes home, and to get it on one slide, I've just summarized this and said something to the effect of, I'm tired. Student, how are you tired? Physically, mentally, or just bored? Okay. Subject. But put yourself in the position of the subject. Okay, your spouse has come home and you're having a nice discussion after a meal, and this is what's going on. I don't know, physically mainly. Student, you mean that your muscles ache or your bones? How are you feeling? Subject, I guess so. Don't be so technical. Okay, then the student actually sort of put in the transcription that they did watch some TV, and then later, subject. Subject is the spouse, remember. All these old movies have the same kind of old iron bedstead in them. Student, what do you mean? Do you mean all old movies? Or some of them? Or just the ones you've seen? Okay. Are you still married? Okay. Subject, what's the matter with you? You know what I mean. Okay. Students, I wish you would be more specific. Incidentally, this is one of the longest ones on record. I'll show you one of the typical ones in a minute. Subject, you know what I mean. Drop dead. Okay. That was, the subject there was about as forbearant as any that you're going to see on this day. This was a very patient person, right? They let this go a long way. This is more typical. Okay. Okay. The subject says, how are you? And the student says, how am I in regard to what? My health, my finances, my schoolwork, my peace of mind, my... At that point, the student gets no further because the subject just loses all control and says, look, I was just trying to be polite. Frankly, I don't give a damn how you are. I'm going to leave it to you whether you try this with your class, but if you do, don't do it because I advised it. Okay. The advice is don't try this one at home. Okay. And it goes on and on. It's great fun. And then, of course, you realize that, you know, that's the way we are. We can't tolerate this. We might think that these rules are so plastic that there's not a hope of mathematics applying, even if you call it soft mathematics. But when you look at it, no, it ain't so. These behavioral patterns are actually very constrained. Not quite as much as planets going round in ellipses and so forth. Okay, that's very precise. Mathematics can really rule the roost. It's not that level of precision, but by golly, it ain't as far away as we might think. I think there's a real chance of applying, not applying mathematics, but of applying the mathematician's technique of looking for the patterns, describing them with algebraic symbols, seeing what symbolic patterns emerge, comparing the symbolic patterns from the sociologists and the psychologists and the linguists, comparing them on the basis of the comparisons, talking to the psychologists and saying, look, you're doing this, it's very similar to what these guys are doing over there. In other words, another use of soft mathematics would be facilitating the communication that we so badly need between different people in different disciplines. And as I say, this is just one of very many of these things.
Up above there? There's some people
I
there.
was wondering if you could speak about poetry and how that relates to math and logic, or how math and logic relate to poetry.
I could certainly speak to it. Can I say anything useful about it? Poetry certainly taps in on some, as does music. It taps in and resonates with our mind. There's something about it that immediately captures us. So when we recognize certain things as poetic and certain things as musical, it's like recognizing that something's a sentence. We can sort of say, that's nice music, that's not musical, that poetry sort of resonates, that doesn't. So yes, to that level, we're in the same ballpark. How much further you can take that, I really don't know. I think I better stop on that one because I simply don't know how much further you can do. I know there have been attempts. I mean, even Aristotle tried to use mathematics to look at the structure of drama and poetry and so forth. This has been done. People have certainly tried to do this. And indeed, if you look at the sing-song patterns of language, the prosody of language, then you do use that kind of information in trying to design speech recognition systems, trying to design computers that produce speech. There, it's important to capture in a very precise mathematical way, sort of sing-song patterns of language, resonance patterns. But in terms of sort of getting into poetry, and I think what the question's saying is, can we write down symbolic rules that will capture what we recognize as poetic in the same way we can capture the structure of a sentence? And I don't know. My guess would be no. But you know, maybe 2 years from now, another Chomsky will come along and give me a surprise.
Okay, is there one over here now?
I always, something always catches in me when I hear people talk from Darwinian thought, and I can't wait until we get to the next paradigm, because I just don't buy it that we're just here to reproduce ourselves, you know? I mean, I know it's more than that, but even that is the central thing. And I've been learning some of Thomas Berry's work and Brian Swimm's New Cosmology and the universe story, and they speak of the human as the universe's attempt to look at itself, or not attempt, but we are the flowering of the universe looking at itself in a self-reflective way. And when you were talking before with the MC person, and you were talking about that the computer, artificial intelligence having as somehow its goal, its self-preservation or replication of the species. I'm just curious, what would an artificial intelligence system look like if the premise that you were going for was that its goal was to be ever more self-reflective?
I guess the simple answer is I don't know. I suspect that we actually, at this point in time, probably have a look at things from a different viewpoint, because I actually, when I try to make sense of things that are going on that I see, I find myself getting pushed more and more towards a Darwinian explanation. I find difficulty okay. There's a corollary, by the way. Okay, so let's not get too excited. I have difficulty figuring out the only way I can get at the notion of meaning, when I start to unpack meaning, I find forces me back into a very ultra-Darwinian form, actually. I can't understand how anything can mean anything from a scientific viewpoint without going back to that point. However, if there's a meta-message to what I'm saying, and I hope the meta-message has come across, it's that, by golly, we run the risk of hammering ourselves to the ground with big nails through our feet if we stop talking to each other. If I disagree with you at this moment in time about whether the Darwinian approach is the right one or not, and we stop talking as a result, then I think we're running a very grave risk of missing the boat, because the answer might be found in blending what on the face of it look like two different approaches. It might look to us now that the sort of the Darwinian camp and the non-Darwinian camp are poles apart, and I think now they are poles apart. But the answer might be found by bringing things together. Bringing things together that are poles apart can sometimes produce, well, sometimes it produces a very dangerous explosion, but sometimes it produces a useful explosion. If we contain the explosion in 4 cylinders, we can drive places. So bringing things together that don't mix well and cause an explosion can be very useful. So right now I think we probably disagree about the main premise, but I hope and pray that that doesn't mean that that camp and this camp stop talking to each other.
Thank you.
I make a very brief editorial. It's not going in the direction of the Brian Swim thing, but the last speaker, Stuart Kaufman from the Santa Fe Institute, are what I would say are proposing a fairly major modification or development of the Darwinian point of view, which is pretty significant. So if you guys anybody's kind of dissatisfied with it but doesn't want to abandon it, it's quite a nice, it's very important stuff I think they're doing, which may be one of those bridges to some other stuff too, but that's not what they're doing specifically. Whose turn? Yours, yeah?
Yes, I sensed a sharp turn in your talk towards the end, and that we were on a 2,000-year path to sort of get to the essence of the mind, excuse me, with mathematics, and then we hit this wall of logic, etc. And now the goal is, let's give that one up, because we're not going to figure it out, but we do have minds, even if we don't know what they are. Let's figure out how to use them better. So, and in that way we can sort of say we understand it, and that if we're making progress, then we're doing something right. But the goal is not really to get to the essence of the mind anymore, but to more amplify this power that we have, but we don't know what it is, which is fine. I'm all for it. The second, I wanted to know if that was a correct reading. And the second question I had is, you mentioned geometry early on, and then at the end you talked about politicians and public speaking and so on, and how Aristotelian syllogisms fed into the discipline for public speaking, but it's also true that geometry did, and that public speakers were trained to imagine themselves walking through a building and memorizing certain rooms and so on. When you walk through it mentally in the process of your speech, you see things that you've put there on the bed or whatever, and it reminds you to talk about this, that, or the other. That's a visual kind of thing, and I think one of the costs that you didn't mention when you kept pulling up the cost, is that all this focus on algebra and syntax and Chomsky-style lexical picture of language, as if language is nothing more than type fonts, gets you into a mindset where you lose your ability to visualize and be very geometrical. And I wondered if part of this soft mathematics and recovering the power of the mind, in your mind, might have something to do with geometry, or where do you see that going? So there were two questions. I'm sorry if they were convoluted.
Okay. The answer to the first question is I actually mentioned two goals. There was the engineering short-term goal, which is the one that I see progress towards right now. And I can see that, I mean, it's not that I'm projecting progress. It's actually out there. People have been doing this kind of thing. These kind of things have been happening. I also mentioned a long-term goal, and I said that would still be a science of the mind. And I mentioned that very often science lags way, way behind the technology. The technology happens, the science follows much later. In fact, right at the beginning of the talk, I talked about calculus. If we think of calculus as a technology, a conceptual technology, that also followed that paradigm. The ability was discovered first. The understanding, the science of calculus took 200 years to develop. The second question was the geometrical aspects of reasoning. And the moment you said that, of course, a thought popped into my mind that, you know, with Apple now in trouble, we sort of make jokes about it. But I remember when the Macintosh appeared. And boy, was that a breakthrough. I mean, to me, that was the most remarkable thing, because suddenly machines were there that people could use. It went from giving commands through language, X, Y's, and Z's, and strange vocabulary, to manipulating things with our hands, or at least feeling as though we were, pulling icons around, moving things around, opening things, closing things, the manipulable interface. I remember when I saw that, being blown away by it, just as I understand Steve Jobs was. It made him a fortune. It cost me a fortune because I went and bought the darn things when they were still $4,000. Then I've been spending money upgrading them ever since. And I remember seeing lots of people who previously would have said they were non-techie, non-computer types rushing out and buying these things. And that, of course, is very much visual. And now we have the new generations of interfaces, which are very much as the gentleman described, where we sort of think of as going through rooms and opening drawers, opening doors, going here, going there. We're now indeed learning how to build those metaphors, those geometric metaphors, into the way we design systems to make them easier to use. Because let's face it, we have evolved over hundreds of thousands of years in order to make our way in the world, to manipulate things, to open things, to avoid danger, to see things. Manipulating abstract symbols is at most 2,500 years old. Arguably, it's only 150 years old if you mean genuinely abstract representations. So we've got creatures who've evolved to deal with space and geometrical aspects without the algebra. Then we've got the algebra, and to try to force people through algebra when their instinct is to use geometry is, in some ways, it's a forlorn game. I mean, it's not going to work. And that's why, of course, interfaces and systems now have much more easily accessible interfaces. So that's a sort of modern twist on the gentleman's point.
Okay, somebody up above there?
Yeah, you've touched on this in a couple different ways. It would seem that the way that we think and our success in reasoning is very much the result of the way our brain has evolved. And you didn't really talk about what's happening in evolutionary biology or sociobiology. And I'm wondering if you think those fields hold any promise in helping us to figure out reasoning, particularly the way emotion, the role of emotion in reasoning.
The answer is, it'll be a gut reaction, because the reason I didn't go into any detail was I know almost nothing about them other than what I read in the same books as perhaps lots of other people do. So I read that stuff and I try to follow that stuff, but I don't have any expertise. I mean, I've trained in the culture of mathematicians. I can look at things in a mathematician. I can't bring biological expertise. I can't even bring physicist expertise. All I can do is look through a mathematician's eyes. I haven't been able to see in any of that work anything to which I can sort of bring that pair of eyes usefully to bear. Maybe that's because that work needs further to go. Maybe it's because I need to change myself. I don't know. But the reason I didn't mention it was not because I didn't think it was relevant. I have no way of knowing. I don't see how anyone knows before we do it what's going to be relevant and what's not. If I had to put my money on it, I would bet that it is relevant. My guess would be that we can't really understand the mind unless we do take real account of the stuff that it's made of and the way that stuff works. Another book that I would recommend to people to read, which is a nice, easy introduction to an interesting field, is Edelman's book. What's it called? Bright Fire, The Brilliant Mind, Bright Fire, or some Brilliant Air, Bright Fire. I think that's it. Brilliant Fire, Bright Air. Those are the words. I mean, there's only 4 of them. Permute them, there's only a certain number of possibilities. Very nice book. He developed something which he calls, I think it's neural Darwinism, which he says the way to understand the brain. He's also someone who says, don't think of it as a computer. He says, think of what's going on in here as a miniature Darwinian system. That you've got evolutionary pressures, everything competing, and that conscious experience is the stuff that sort of filters to the top at the moment. It's an interesting book. It would be pointless for me to try and say any more about it than that, because he says it very well in his book. He's the expert in that field. I'm not, and I'm not even going to try to say more about it.
Okay, I think we're here now.
What is the relationship between what you're calling soft mathematics and what I remember reading a few years ago about fuzzy logic?
The answer is the relationship is almost zero, and let me just fill in a little bit of background. One of the things about logic is it's very black and white. It's something that my wife has complained to me about many times. You're too black and white. Everything's yes or no, right or wrong, and she would say that the world is full of shades of grey. Okay. Logic works, and mathematics work, because we assume yes, no, plus, minus, yin, yang, 2 alternatives. And that's how we develop logic. That's what enables us to build very fancy computer systems, because we can have the circuit is on, the circuit is off, the voltage is above this threshold, it's below that threshold. So classical logic is yes, no. It's what we call two-valued. Suppose you want to extend classical logic to allow for these shades of grey. One way to do it is to say, let's have something being false or as being 0, and let's have something being true as represented by 1. And instead of just having 0 and 1, allow things like a half, a quarter, 3/4. Something is a quarter true, it's a half true, it's 3/4 true. That gives you a certain degree of plasticity. It gives you a degree of fuzziness. It can possibly be useful to do that, and in fact it has been shown to be useful. People have used this machinery in order to design systems. You have things called fuzzy focus cameras, which sounds very amusing, because surely what you want in a focus is a sharp focus, and what Japanese manufacturers discovered, you could get sharp focus cameras by having what was known as fuzzy control, and control of sort of, I don't know, I think subway systems and so forth. Interestingly enough, there was a debate, and I think it's still unresolved, as to whether fuzzy logic was really what was making it work, because typically the Japanese manufacturers, and this tended to boil down to the Japanese and the Americans, the Japanese would say, yes, fuzzy logic is what's making it work, and the engineers in the States would tend to say, we just call this feedback mechanisms, we just have a feedback, we sort of take account of the changes, fuzzy logic's got nothing to do with it. That being to one side, the issue is whether you get a genuine conceptual advance by fuzzy logic. I don't think you do, because all you're doing is moving one step nearer to the moon. You're going from 2 values to say a half or a quarter or 3/4 or even the entire rational or real line. You're still demanding precision. You're demanding precision 1 step removed. And I think all of the things I've been using in the examples towards the end indicate that it's not that the precision is hidden from us. There is no precision. Mathematics works by finding the right level at which to apply some kind of precision. And I think to apply it at the level that we do in fuzzy logic, and it's a very nice piece of mathematics. And incidentally, as a general point, I should say, nothing which I've criticized tonight do I think was a mistake, in the sense that society advances by trying things, coming up against walls, trying something else, coming up against walls. That's surely all to the good. So I'm a fan of AI, I'm a fan of expert systems, I'm a greatest fan in the world of Chomsky. So all of these things I think are great, but there's no perfect answer. Going back to fuzzy logic, It gives us something that we didn't have before. I don't think it gives us very much. I think there was a lot of hype that went beyond what it gives us. But I don't think it's getting to these issues, because in these issues, it's not just that the precision is slightly removed. It's not the distinction between 0, 1, and allowing intermediate truth values. It's that there is no precision at that particular level.
Good, great answer. Over here.
When I think about children and their ability at the early ages to apprehend language, culture, context, other forms of context, emotional context, what I think I see is maybe the ability to go beyond the wall that we try to get to with the computers. So if I use the venture capitalist example and exercise their minds and limber them up by transplanting them to different cultures, for example. I'm going to take this to an extreme, and something I'm not going to do. And go from culture to culture, they begin to see those as things external to themselves, something that they can then manipulate and begin to fulfill the short-term goal. Now, logically, you could subject them to different emotional states, to different cultural states, and so on and so forth. Before I go and take my kids to India or wherever for short trips, has anybody gone off and looked at this and looked at the abilities or look at the backgrounds of people who have made the leaps and put together any kind of a theory of what you can do to limber them without breaking them, to sound a little harsh perhaps, to get there?
I don't know, and if there's anybody in the audience who does know, please send me an email or send me a message and let me know, because that's the kind of thing I'd like to know more about if it happens. I don't know. If there has been a systematic study of different effects of culture taking people around, please let me know, because the next time I give a talk like this, then maybe I could give a more coherent answer. But right now, the only answer I can give is I don't know if that's been done or not.
Okay, up above.
I was curious, you spoke about soft mathematics, and it struck me that in a sense you're looking for a different level of patterns and things, and that chaos theory in a sense was an attempt, or is actually a means of looking at rather chaotic things, and sometimes I think we look at culture and language as a very chaotic phenomenon. As an example of a sort of soft mathematics, and what do you think about that as a paradigm?
I would be inclined not to classify that under soft mathematics. I think what we've got there is another direction that you can take hard mathematics. Typically, we get our mathematical patterns mostly because we work at the level of linearity. We work with linear approximations, maybe quadratic approximations. We tend not to go to higher orders of complexity. And the amazing thing is that buys us an awful lot of progress, both scientifically and technologically. So we look at the simple approximations, and in the physical world, that works. Other ways that we can now go, and people are going, and this is a completely different path from what I'm calling soft mathematics, I think, and it's possible because of large, powerful computer systems, is we can go into nonlinear systems, we can go into the complexity theory, we can go into dynamical systems, we can investigate those in ways we couldn't before. Previously, if you were doing physics, for example, and you had a differential equation that governed some kind of a flow, what you did was you sat down and you solved the differential equation, you got a formula, and then you looked at the behavior of the formula, you do a graph. Now you can use powerful computers where you don't, and the trouble is most differential equations that arise in the world can't be solved that way. But now we solve them in a different way. We don't find a sort of what we call a closed form solution. We just graph all of the family of solutions. We see what the flow is, what the vector fields is. We get a visual understanding. I would say that we actually get a much better understanding of the domain by doing that, because our mind is very well adapted to understanding visual representations, as opposed to figuring out the meaning of a formula. So those are different paths. Those are paths that I would say are still very much in the paradigm of hard mathematics. It's sort of hard mathematics gotten even harder because of the power of computers. I may be wrong, and then things may tend to blend with each other, but right now I would call that hard mathematics very different from soft mathematics.
Okay. Over here.
I'm afraid my question is going to be